Hello, everybody. Welcome to the last talk of track 2 for day 1. We really appreciate you being here. It's been a long and really good day. For those of you on the East Coast, it's almost 7 o'clock at night. And for those of you on the West Coast, it's 4 o'clock in the afternoon. I think, right? So that's how math works. So we're here with Phil Young. Phil's going to give a talk called Not Just Evil, Hacking Mainframes with Network Job Entry. Thank you for being here, Phil. Go ahead and take it away, and I will come back, and I'll be here if you have any issues. So feel free to ask.
All right. Well, thank you. Thanks for having me, everyone. This is a talk that I've been wanting to do for a while. So before I get started, I have to always put the disclaimer. I'm not here representing my employer or speaking in the name of my employer. So there we go. Disclaimer out of the way. Okay, so this all, in fact, most of my mainframe hacking career started when I was working at Visa, and I saw a developer create a new user on one system, but like they're on a dev system, and that user was created in production. And I was like, how is this possible? Like, how did you do that? They didn't SSH in, they didn't have like remote control. And it looked like this. This is exactly what it looks like. So they have this JCL that they're going to use, they're going to submit it, and it's going to add a user on this other system, and it runs, and then you get some messages that it came back and it ran successfully, and now that user is created in production. So how does all that work? That's what this whole talk is going to be about. So a little bit about me. I put hacker here, but I was an X25 network adventurist, explorer maybe. I worked help desk for a major Canadian TV network for a bit. I used to be an auditor for one of the big 4 audit firms. And then I worked at Visa for about 5 years, which is really where that kicked off sort of my passion for mainframe cybersecurity, because it was there sort of how I saw how bad mainframe security was at the time. Like everyone, like up until then, everyone was always touting how safe mainframes were and how secure, and they were unhackable. And then I was able to get my hands on my own. And then from there, I was just like, well, it's not really. It's just that no tools exist, and the information's not out there. They're hackable. It's just no one knows how. I've spoken at a lot of conferences, except for the Chaos Computer Congress, because I'm not going to Europe between Christmas and New Year. Okay, so I also teach a class with a good friend of mine, Big Indian Smalls. You may know him. He is the world's #1 mainframe hacker. I teach a class called Evil Mainframe with him, where we bring in an actual mainframe, and it has labs. So the first day is focused on how does the mainframe work, and the second day is how do you hack the mainframe, and then there's a CTF with everything you learn. We're teaching it at Black Hat this year. We're very excited. This talk, like I said, this is a talk I've been wanting to do for like 3-4 years now. It's a very technical deep dive into network job entry. It's based. I posted in the Discord already. If you want to keep up, if you want to follow along, there's an article I wrote many years ago for POC or GTFO 212. So that issue covers sort of all of this talk, what we're going to talk about. It doesn't have some of the demos, it doesn't have some of the information, but sort of keep up if you want to read after the fact. We're going to talk about job control language. We're going to talk about network job entry. We're going to talk about trusted nodes, and then we're going to talk about node takeover with a Python library. Job control language. This is probably every talk I give, unless I'm talking at a mainframe conference, I sort of have to give a primer on job control language. It is the most important component of sort of mainframe hacking. You can avoid it as long as you want, but it's very important. When I'm talking about mainframe, I'm not talking about AS400. So I'm not going to be talking to you about AS400s. I'm not going to be talking about Unisys or HP Nonstop. I'm going to be talking about z/OS, sort of like the IBM's flagship mainframe operating system. It is a current day modern operating system. When people hear mainframe, just like before this talk, when people hear the word mainframe, they think, oh, it's like giant spools of tape spinning around in a closet somewhere. That's not the case. These are very fast, very purpose-built machines to handle transactions at speed. When I was at Visa, one mainframe could handle all the global processing for every Visa transaction around the planet. Just one box, right? So it's very powerful. It runs a whole bunch of things, but okay, so it runs TSO, which stands for time sharing option, and this is the bin bash of z/OS. I'm not going to spend, I have given so many talks about TSO and navigating TSO. We're not going to talk about TSO at all, except for some of the examples that we use JCL, but know that it's like a bash shell. So like you run commands and you get responses back. Kix, so you might have heard Kix or CICS when it comes to mainframes. Maybe a Kix web transaction server, or somewhere in the back end there's a Kix JSON server. You know, you can do queries and API calls or REST call, whatever you want to do with that. So that runs on the mainframe. So if you've interacted with Kix, maybe this is something you didn't know was running on the mainframe, but Kix, CICS, and then JES2. So JES2 is pretty much what the rest of this talk is almost about. We do talk about JCL a lot, but JES2 is sort of the most important part of the operating system today. So JES2 stands for Job Entry Subsystem. There is a JES3, but it's not owned by IBM. So while JES3 does exist, it's not really like Python 2, Python 3 in terms of like, oh, it's the same people. No, it's a totally different product made by different people. IBM owned it for a while, and they're getting rid of it now or they just sold it. So basically, you have this job entry subsystem, and jobs are submitted to the job entry subsystem, and they queue based on their priority. So you have jobs that are higher priority. So say you have payroll at midnight, and that payroll needs to run no matter what. Well, that will have a higher priority than Phil wants to add a new user so that when they show up in the morning, they have an account. That can run anytime. JES is handling the input and output. So you tell it where the input's going to be, you tell it where the outputs are supposed to be, and it sort of handles all that setting it up and setting up the memory and stuff like that. This is a pretty good diagram that explains JCL. So when we get to the actual jobs, you'll see in a minute, it's called a job card, especially the first. So every line of a job is actually a card. That's why this picture here is of cards. So you have like a whole bunch of cards that explain. Now this is an old holdover from back when they used to use cards. They don't use cards anymore. But when you write your JCL, you put / and then whatever you want to do. And that's almost like a new card in your stack. When you've written up your JCL, you put it in through JCL, the JCL interpreter. It interprets it. It pulls in like it'll do. So sometimes you have like symbols that you have in there. You can set symbols. You can set variables. And it does the interpretation, and it makes sure all the syntax is going to work out, right? So it doesn't bother running it if the syntax isn't going to be good. Other times, like you might have rules that say only users with this user can run jobs. This is where it's going to get checked. And then proc_lib, like you might have procedures that you pull in that fill in a bunch of things automatically in your job. So that's where you would have like a proc_lib or a procedure, get that pulled in as well. And then it goes in the queue. This is all run by JES, right? This is all run by JES. You put it in the queue, and then once it gets to the queue, it goes and executes, and it pulls in the data sets or Unix files or inline. You'll see what inline is in a minute. But it pulls all that in, does what it needs to do, and then spits out the output. You can have what's called steps. You have multiple steps in a job that has input and output, and one job step can lead to another job step. But this is like a high-level overview of JES. We have the job control language. So each job is made up of a job card, then the steps, then the input and output for that step. And there's so many forward slashes. There's a billion. I've heard the rumor that like it has forward slashes because it needed a way for the card reader to grip. I don't know. Look, it's full of slashes. Okay. So here's an example. Now I already know because I wrote this before I took the screenshot that this one won't work. This job won't work because it's missing a comma somewhere. But you can see there's slashes on every line except for the sysint. So here we're going to walk through this piece of JCL right now. So first we have the job card. So this is the high level, like the first thing that it needs to process. It's got the job name. It has the word job. It has accounting data. It has the name of the person running it. And like if you want to read the details of what all this does, the tutorial point has a really good primer on the job card and all of the things you need for a job card. But that's the job card. Now notice I have commas that do line continuation. I am missing a comma at the end here when I took the screenshot, but know that in the later demos you'll see a comma here. But basically it means you have this job that is owned by, this is job name, and this is the comma, and it's owned by this person. Next you have the step. So this is the job step that's going to run. This is the first step. You can have multiple steps, but this is really the first step that's going to execute once that job gets submitted. I called the step run CMD. You could call it whatever you want. I was just being clever. You could call it step 1. You could call, now mind you, you can only call it something that's 8 characters long or shorter. You can't call it anything longer than 8 characters. So you would have like a job 1, 2, 3, 4, 5, 6, right? You could have, maybe it can't start with a number, but you can have all kinds of things as long as it's not less than 8 characters. And then you have an execute, and then you have like a program, and the program here is the program that's going to run. So we're going to execute program, and the program is called IKJEF01. Rusty skills, yes, I'll make the slides available after the talk. And so IKJEF01 is a program that runs commands in TSO. So this is a job that will run commands in TSO. Next, we have the output. Where is the output from our job going to go? And right now, we're just pointing it to sysout, which is like a log, and you can go view the logs for all your jobs. And then you have the input. So systsIn is kind of like, it's like a flag. So here's the input, and now this is inline data. So you see that star, and then we have the commands. We're going to run lu and listcat. Okay, these two together. Imagine, so like when I explain this to people, imagine this is like I'm on Bash and I type IKJEF01 space dash systsPRT equals, varlog space dash systsIn equals, and then in quotes these two commands. Right? That's how you sort of read this if you're coming from like a Linux, Unixy type world, which is where I came from. But that's how you have to understand this. There's all kinds of things you can do with jobs that are really impressive. You can submit jobs to other users. So here, for example, we put in the user equals plague. Now, there are controls in place, so you can't just submit a job as any user on the planet, right? You have to submit jobs that you're allowed to submit users as. This is called surrogate authority in RACF. If I put user equals plague and I don't have the authority to submit jobs as that user, then the job won't run. It'll come back and say access denied. Unless I add the other option here of password. I can put user equals plague, comma, password equals love, and now I can submit jobs as that user. But we'll see that's not always the case as we start talking about network job entry and how we can take advantage of that. So you saw already, we saw those DD statements. Let me go back here. You see this DD here, right? These are called data disposition. And that says, like, where is the input and where is the output? So like if you say, if it's expecting data, then the DD sort of defines where that data is going to come from. So you have like DSN equals some place. So like say, for example, I'm going to do sysout. I'm going to do this at systsPRT, which stands for print. I'm going to put that in a file called, so DSN equals dataset name equals wildwesthackandfest.jobout. Like that's where I'm going to put the output. Instead of putting it in the log, I'm going to dump it there. You could put it to a temporary data set, and when the job is done running, that temporary data set gets destroyed. You have sysout equals, that's like the output log, and then you have star, right? Star means anything. Now you can't do star for output, but you can do star for input. And that means basically anything until it hits another job card, like a // just read it as inline data. There's all kinds of fun programs that you can run in JCL. The IEB Genner is like create, move files, do all kinds of cool stuff, copy, delete. BPX batch is execute commands in Unix. I don't really have the time in this talk to get around, like talk about Unix in detail, but know that Unix is part of the ZOS operating system and it controls networking. It's a part of the operating system. It's not like a VM or something. And then ISR supc, which stands for super C, which is a diff and grep married together. So if you want to find like the word password in a bunch of data sets, you would use super C to do that search. And then finally, IFBR14, which is the NOP of JCL programs. It literally does nothing. It just returns 0. It has no function other than that. But that exists because then you can do things with input and output data like create new data sets or copy a data set or delete a data set. Like I don't want to, then I'm just going to use IFBR14 to do some stuff. Once you have your job all set to go, once you've written it all up and it's ready to go, you submit. When you submit a job, it runs as your user ID. Inside the operating system, there's a job header that says, this job was submitted by this user. In NJE, we'll talk about that header when we get to it, but that's how it runs. So you submit a job, it runs as your user ID unless you have the user equals, then it goes in as your user ID and then checks, is this user allowed to turn into this other user? And if not, then no, they can't do that, right? And then you just type submit in TSO. You type submit and it goes. So this is going to be an example of us submitting a job, submit. So here's a job. It just lists my user ID like a who am I, and then lists the catalog, which is like an LS almost. And now we're in SDSF, and now we can view the output of the log here, and if you go to the output of the step run CMD, you can see there's my user ID, and here's a whole bunch of information that's running in this script, right? So it's just running TSO commands, running NSJSF. Now, JCL is very powerful. Most people are surprised to find out that you can run a high-level assembler through JCL through Metasploit, like from Metasploit. So if you have Metasploit on your system right now, you can look up this exploit. It's the FTP one, and you can actually generate high-level assembler payloads that will run on ZOS through like using JCL. So it'll create JCL, and in JCL you have like compile, link, and go JCL, which will compile the program, then link it, and then run it, and then delete it from memory when it's done running. So here's an example of Metasploit using FTP creds, getting a reverse shell on a mainframe. Super. I mean, so long as if you have FTP credentials to a mainframe, you can get a reverse shell. This was done by Big Endian Smalls as well. He wrote this module for Metasploit. He did all the work here. But again, that goes by real fast. So I'll show you the two again. Here we go. We're connected. This is a bind shell that I used, and now I'm running as user Phil, and I'm running on ZOS. So you can see I'm running in ZOS. To summarize about JCL, because it's important to understand JCL as we get, because that's what JES does, and network job entry is running on JES. JCL is used to control jobs, how the steps and input and output. You can run TSO and or Unix commands through JCL. You can compile code, and it runs as your user unless you put user equals in the job card. So that's all you need to know for this. Now, I don't see any questions in the chat, so I'm going to keep going here. If what we've talked about so far wasn't dense, then good, because it's about to get even more dense. When I submitted this as a very technical talk, so buckle up. So imagine, if you will, you're at a corporation and you have offices in Miami and Orlando. And you have some data in Orlando that you want to do some work on, but you're connected locally to the mainframe in Miami. So you're going to use network job entry. This is what it was designed for. It was designed so that if you have local processing power, or you have a smaller machine, you have a bigger machine somewhere else, no need to connect to it, just submit the job, and then it'll come back when it's done. Right? So here's an example job. Again, IKJF01, going to be running a command LU on a different system. The important thing is here that it's going to run in Orlando. So here we are, map of Florida. We have one mainframe, we have another mainframe. I'm going to send a job up. So that job that we have here, it's going to run on a target system called Orlando. That's the name of the system that we're going to run it on. So we have Orlando. It's going to go up to Orlando. It's going to do what it needs to do, and then it's going to come back with the results. That's all network job entry is really doing. So that's network job entry. The way it works is what we're going to talk about in a few minutes, but know that all it's really is for is I have a job, I want to run it somewhere else, and then get the results back. And most companies have more than one mainframe, and so they use network job entry to control all the different mainframes instead of having to log into like all 10 of your LPARs. Some terminology that we have here. So NJE stands for network job entry. You have the node, which is the name of a system running NJE. You need to know the node. You have our host, which is, so if I'm Miami connecting into Orlando, then the R host would be Orlando, and my O host would be Miami. Does that, like that, it's always confusing to me. I always get it wrong until I look it up. But R host and O host are very, very, very important. Okay, so how does it work? So first you got to set it up in JES2 on both systems, and then we're going to talk about the protocol, and then we're going to talk about a Python library that I created to make working with NJE easier for everyone else. So first, JES2 runs on TCP/IP. I mean, it also runs on SNA, but most people run it over TCP/IP. It needs to know its own node name. So it has its own node name. It needs to know, and it needs to know where to connect and who to accept connections from. That's really just done in a simple config. So you have this is it. This is all it takes to run network job entry. So you have how many nodes you're going to have, the node num, your own node. Like, what's your node number? Are you node number 1? Or are you node number 10? And then how many lines do you have? Do you have 1 line? Do you have 10 lines? And then you're going to define the nodes. So in some places, so for example, the reason really this kicked off is because when I was at Visa, they had a whole bunch of nodes in here, and a bunch of them were were decommissioned, but they were still running inside the environment, right? So they were still waiting, like the mainframe, like NJE network was waiting for connections from those systems, even though they didn't exist anymore. So you have your nodes, so node 1, node 2, and then NetServe, you set up, the sockets and whatnot. And in the bottom here, socket water, node 2. So we're going to use node 2 to connect to this IP address. This is not whitelisting. This is not a way to say if only accept connections from this IP address. That's not how this works. What this is saying down here, what the IP address equals down here, is when you're ready, I will try to connect to that system on that IP address. But if it comes from any other IP address, cool, even better. Like if it connects in from a different, like a 10.10.10.10, cool, I'll accept that connection, right? So it's not whitelisting. It just, you can also add other things in here like a password. So in the config file, there's a password that you can set. You can also set it up to use TLS security if you wanted to. You can also, the best way to do it really, if you're going to set up, if you're looking at NJE, is you really want certificate authentication, right? Lots of places don't have any authentication. If they do have authentication, it's authentication with a password, but the password is in the config file, so you can just read it. And lots of places say, oh, read only, that's not a big deal. Who cares, right? That's all you need to set up network job entry. Starting it up, I'm only putting this out there in case anyone really wants to do this at home. Very rare, but this is what it looks like when you start it up. So you start up, you turn on all the communication protocols, and then you say, I want to connect this node on line 1 to the mainframe water, and then it'll start going, right? So we have these 2 nodes here. So if I'm smog, it'll connect into water. At this point, it's just listening. So if water didn't exist, it tries to connect like 3.1, like whatever, 3.3.3.3, and it doesn't exist. So then it just waits, and it sits and it listens on port 175. Back in, let's see, do I talk about the, yeah, okay. So back a few years ago, I wrote a probe for nmap, and then IBM pushed an update, and now that probe doesn't work anymore. So just know if you're on port 175 or 2252, that's likely NJE on the mainframe. Okay, now, time to get real into the protocol for network job entry. This is the sort of the stack. So also on top of TCP/IP. So you have all your TCP/IP handshakes and session handling and all that stuff. But now we're going to talk about, I see your chats beginning and smalls. We're going to talk about the open of the connection, sending all the data, and how we used to use a response for the open handshake to do brute forcing and stuff. But looking at the I record, so there's all kinds of control records, and then TTR, TTB, compression, all this stuff. We're going to talk all about this in the next like 20 minutes. So first, we have to connect on port 175. And unlike most protocols, you connect, there's nothing. There's literally nothing. There's no information. All you have is an open socket. And if you send garbage data, it doesn't send any data back. You have to send an exact initialization packet to get everything moving, right? So that's called the connection request. Right? So when you open up a first connection, you have to send a packet that is 33 bytes in length exactly, and it has to have all this information in it. So you have to have the type. Am I going to be open, ACK, or NACK? What type? Like, what's my name? Is it Miami? Is it someone else? So say, for example, in another example, water and smog, and I'm water connecting into smog. My R host is water, and the O host is smog. And then we have our IP address and their IP address in hex, and then the reason code. Back in version 113 of ZOS, the reason code would come back different so say, for example, there used to be a way to brute force a mainframe's O host, because the reason code would come back with a 2 if you got, so like it would assume, I guess, that you had flipped the O host and R host in the submission, and would come back and say, oh, the reason code is 2, and that reason code meant you've swapped, you have the right information, you just have them backwards. So you could use that to brute force the O host of a system. Can't do that anymore because IBM silently fixed that. But you can still brute force, if you know the system's O host, you can still brute force it, R hosts that exist. Looking at it with Wireshark, you can actually capture this in Wireshark. So if you're using the clear text protocol, this is what it would look like in Wireshark. A lot of acts. I know, because Big Enny and Smalls is watching, that he already knows that this is EBCDIC because there's lots of 40s which is at an ASCII. And I know that, like anyone who does anything with the mainframe and looking at hex, you know that if you see a lot of ats, chances are it's EBCDIC. So when that happens, I just go into Wireshark and I turn ASCII off and set it to EBCDIC. You can see there's EBCDIC right here, and I'm just going to turn on EBCDIC. And now I can see that it's water communicating, trying to open up a connection to Smog, right? So this is the initialization handshake, like this is the initialization packet to connect into a mainframe NJE session. So what we send it open, and then it sends an ACK. If it doesn't work, if you have the wrong O host or R host or anything wrong, it'll send back an ACK, right? So you can use that to your advantage to try to brute force things if you know the O host. Next, we send what's called a start of header and an inquiry packet. There's a bunch of other stuff that goes into this packet, but we have to send a start of header and an inquiry. But before we do that, we have to start building. It's like stacks on top of stacks. So you have TCP/IP, and on top of that runs NJE. So everything in here is controlling the length of data, length of headers. So we have a TTB and a TTR. And the name, I say these are really not, they're documented what they do, like how they work. Otherwise, I wouldn't have these slides. But the name is not documented anywhere. It doesn't, like I tried to like figure out, like I just assume that the B stands for block and the R stands for record. So you have a TTB, which is 8 bytes long, of which it only uses 2 of those bytes, and that contains the length of the whole packet, right? So you have like this packet is going to be X bytes long, here you go, and that's the TTB, right? And then you have a TTR. Each TTB or block can have multiple records, and the records are going to be 2 bytes for length. So you have to have a TTB and a TTR. So this is the next thing we have to send. So we send the open, get the ACK back. Now we have to send this start of header and inquiry, like 2 bytes. But now we got to surround it with all this other information, right? So we have the TTB. So this is 18 because it includes itself, right? So this is 18, and you have this whole length here that includes the TTR and then a footer, which is always zeros. It's always zeros, just 4 zeros. At this point, we can start doing what's called the sign-on request using network connection control records. I told you it was going to get dense. So a network control record is going to be made up I, J, K, L, M, N, or B. Don't care about any of the others. I only care about initial sign-on and sign-on reply and closed connection. So sometimes, like so in the Python script that we're going to talk about later, it sends closed connection because it connects, does its thing, and then it sends the closed connection so that other systems can connect. So an I record is made up of a whole bunch of different fields, but the most important fields within the I record are that password that I was talking about. So you can actually have a password like this is my password and you're expecting this password. So you can send 2 separate passwords in the connection request that are set up in the config. So you can actually set up the config and say my password is 12345 and that system's password is 678910, and it has to know both. When you set up, imagine the nightmare of configuring and setting all that up though, right? So most people don't do that. But if you wanted to, you could try to brute force those. And that's called the I record. So this is the initialization record to connect. These passwords, again, are stored in the config file. And to any mainframers watching this, other than big, and smalls, after the fact, know that whenever I say config file, I mean parmlib, but no one's going to know what a parmlib is if I keep using that term. So far we've covered the TTB and the TTR. From here on out, every packet is going to have what's called like a DLE and an STX. These are just like ASCII control characters. They're control characters. They're in EBCDIC, they're in ASCII. It's transmission control. So what it really means is we got the last message. So like acknowledge, it's like an ACK SYN almost. Like it's yeah, I acknowledge I got the last message. Here comes more data. Okay, that's what that stands for. BCB. So every record, the block control byte, is used to track the current sequence that we're in. This is used so that you can't just jump on and spoof and say, hey, I'm this packet. It keeps strict control of the current sequence of NJE records sending back and forth. when we do but it only starts when we send the first initialization record. So if I connect into a system, my first one's going to be 80, like hex 80. After that, it's hex 80 modulo, like whatever the number is. So like number 10, 12, whatever it is, modulo 16. Right. So when I connect, I start off. So you'll see in a second, like our first initial, like our BCB is 80. As we start doing more communications, it goes up and then circles around. The FCS is the function control sequence. It's 2 bytes long, and it's the current stream. So when you're connected in and you're communicating data back and forth, it just identifies as this stream is this data. That's all that means. It's the identifier for that stream. Now so that's just the header, right? And now we get into the interesting thing. So the RCB, which is the record control byte. There's a whole bunch here that talks about what kind of record is coming up. Do we have, is the start of a stream? Can I start a stream? BCB error. So a BCB error would be, I'm sending in and I think I'm sequence 12, but you think I'm sequence 14, and it'll come back and say, yeah, I just ignored all that, and I'm going to say that you're at a sequence, and we'll renegotiate a sequence. A control record, that's the I record, right? That's what we're talking about now, is the control record. So I'm going to send hex F0 and get, that means this is going to be a control record. And then you have nodal message records, which I'm going to talk about when we get to some tooling, and then sys in and sys out. That's the RCB. Now, every RCB has a source RCB. Why they have two, I don't know, but every RCB must have an SRCB because of IBM. And RCBs can be all kinds of things. So like if you have an RCB of F0, then you would send an I record. If you have like a RCB of 9A, which was control record, then you have a source RCB of 00. If you have like sysin, then it's going to be the type of data that's coming in. And then now the data. This is where it gets really fun, because TTRs have a max length of 255 bytes. Each record must include the RCB and the source RCB, which means we have a max length of 253 bytes for data. So what does IBM do? They implement compression. Except for some NCCR records, they don't need to be compressed, but everything else needs to be compressed. So they create this compression called string control bytes. So what that basically means is you take either a repeating character or spaces, or everything from here to here is just straight uncompressed data, skip X bytes ahead. And I implemented this compression algorithm in Python, and I'm happy to say that mine is 1 byte shorter than IBM's, but that's just how it works. So you have a byte that starts with like 101, and then like 1111 would be X characters repeated X times, right? The following character is going to repeat whatever times. So let's take a look at how this packet looks on like a real life system. So first, we have the I record. No, this is an example of an I record, sorry. First, we have the TTB. So this is the total length of the entire package that's coming across the line. Next, we have the TTR, which is going to be of this length. This is how long this entire record is. Then we have our DLESTX, which is saying, yep, I got whatever message you sent. Here's some more data. Now, remember, I told you the BCB is our first initial handshake, so it's 80. It's zero-ish, right? It's 80. And then we have our function control packets, and then F0. F0 is NCCR, right? That's the RCB. And then the source RCB is the letter I, which is the I record. That's what we're using to connect into this environment. And then notice here, so the rest of it is a whole bunch of headers, but this is where the 2 passwords would be. And I know 40 is space in EBCDIC. So essentially, if you don't set a password, the default password is all spaces, right? Everything is padded with spaces. So when you connect, and if there's no password provided, it just pads it out with spaces. So you send an I record, it sends a J record. Now you're cooking with fire. Like now you're in. Anything from here on out, you've been authenticated essentially to the system. Now we can do a lot more than this, but for the sake of argument, we can do these 2 things. We can do nodal messages, which are JES2 commands. So what that means is I send a command into the JES2 environment of a different system. I can look up jobs, I can look up what's running, I can look up all kinds of stuff. And then, or I can turn off JES2 if I have that authority, right? Like you can control some permissions, but I could submit a job in, I could submit commands in to just turn off JES2 on another mainframe. That would be devastating. Please don't do that. But that's the power that you have. Sysin is we can send one job from one node to another node. So if I'm going to send one job from one place to another, then I can use sysin data. This is where we start talking about NJE. So that's network job entry from a high level. Now we can start talking about like what you need to do NJE hacking. So really, this is a very long list of everything you need to hack network job entry on a mainframe that you have found. You need an O host and you need an R host. That's it. That's all you really need. I mean, you need a little bit more, but you need an R host and an O host. And thankfully, you can, if you know the O host of a system, there's an nmap script called NJE node brute that will try to brute force the names of the R hosts for other LPARs that it'll accept connections from. So here we did a scan against a mainframe, and you can see it'll accept connections from a mainframe. Water will accept connections from a mainframe named Smog or a mainframe named WWHF, right? So if I pretend to be, if Smog is already connected, now only one system's allowed to connect at a time, and they usually stay connected for a long time. So if I try to connect at Smog, it'll just say, no, you're already connected. What are you doing? But if WWHF is not connected, then I can connect in as that system and pretend to be that system. So we know the R host, we know the O host. Let's talk about how we can take advantage of the sysin data. So remember way back at the beginning of the talk, we talked about JCL. And when we send JCL from one system to another, when you submit it in, it records the user that's going to be in there, right? So when you send a job from one system to another, there's all these job headers for network job entry that go into this. You have general, scheduling, job accounting, and security. Security is what we're going to talk about here for a bit. And I'm only, look, for the sake of time, we're only going to talk about 2 headers. There's 19 headers in just the security section, but there's 2 headers that we really care about, the to user and the to group. And if you know that, and on every system that runs RACF, there's an IBM user, and chances are they're still connected to group sys1. You already know a user that's on the system. That's how the job is going to run. So if you can control the NJH2 user and the NJH2 group, you can control what user you're running the jobs as. So all we need is to do this hacking is an O host, an R host, an IP address, a username, and a group. And once we have that, we also need one more thing. We need a mainframe. Right, we need a mainframe to do all this hacking, except that's not true because we can just do it with a Python library that I wrote over many months. So yeah, just go out, quick, buy a mainframe, you'll be fine. They're cheap. You can use this library. It's available today. It's been available for many years, but only beginning and small as I've been using it. It includes attack tools that I built to demonstrate some of the capabilities. You have the injector.py, you have jcl.py, and analyze.py. So injector will send command and control messages. So for example, if I don't know the users that are running on a system, but I can connect in with NJE, I can see how many users are running on Smog. So this is an example of me running injector, and you can see down here, so I run, this is the command that I'm running, so display all TSU. So any job that starts with TSU, which is a TSO job, if I run that command, it'll show me that Phil and Plague are logged into the system. And then I can use the JCL program that will submit JCL as any user I pass it in the command line. So from Kali, this is just Kali, I can run this Python, I tell it the O host, I tell it the R host, so like who am I, who are you, the IP address, and then a user that I want to run, and it includes a bunch of JCL. So I'm not expecting you to write your own JCL. It includes a bunch of JCL that you can run that will do bare bones things. And then the user I want to run this as is Plague. So here we have the example of me. I'll show you a demo since I have time. I didn't know how much time I was going to have, but looks like I got about 4 minutes left. I can show you some live demos. And then analyze. If you have packet captures from a network job entry going back and forth, you can actually extract those, like the packet data, and run that through an analysis program, and it'll show you the output. So here's an example where we had a I record, right? So I had done the packet capture, and I saved the packet data for an I record, and you can see here it's breaking it down into, this is the total length, the record length, here's the compressed record, here's the record type, so RCB is F0, the type, it's an NJE, and it tells you it's an initial sign-on record. And if this had a password in it, you would just see the password in clear text in EBCDIC. Okay, so let's see some demos here of using network job entry. Let's go here. So we already have this all queued up, ready to go. So again, I'm going to connect into a system, see if this works, and then I'm going to connect into a system as WWHF smog on the IP address, and I'm going to run, actually I'll show you what that JCL looks like. Just cat it. Super simple, like it's not even that many lines, but it's 2 jobs, it's 2 steps, it's 1 job, this is the job card here up top, and then I'm telling it, this doesn't really matter, this is just more for performance. You delete that line. It's going to run 2 jobs. It's going to run the Unix command job, and it's going to run the TSO command step. So the Unix command step and the TSO command step. Let's run that. And it takes a while, so it's trying to connect in. So first it's going to connect. It'll take a while. And now it's running. And it's going to wait to get the response back from the system, because it thinks we're a mainframe now. It thinks we're a mainframe. That's part of the node network, so it gives us the reply back. And this is all job information. Like you normally see this in SDSF. It's the job log for this whole job. But really what we care about is down here, where here's the output of the Unix. So if you look at when we catted the program, it's going to run ID, who, and uname-a. So ID and uname, like no one else is running on the system. But ID and uname, so that's the output here, is I am, let's see, I lost it up a little bit. There it goes. So that's the user ID. And the system is smog, and it's running this version of Unix. And then the next one runs in TSO. The next step is going to run in TSO, which runs the LU, and I'm running as user play. I could do that as, let's see if I can remember 0. Cool. See if I put them on here. You could run this as any user. You don't need to know their password, because the way this works is because we've set up RACF. And a lot of places do this where they trust the nodes. All the nodes in the environment are trusted. And so, yeah, so this user doesn't exist. So what that means is, because a lot of places do this, if you authenticate on one system, it's assumed that you're good. And if that user account from that system exists on the other system, then it'll just run the job, right? There's cases where you might have a user named John Smith on one system and a user named Jennifer Smith on another system. And if you use first initial last name, and have NJE, then those users could run jobs as the other user on both systems, right? Because it's just using the user ID to submit those jobs. Let's see if I have an example of injector here. Yeah, okay. So I'll show you what that looks like. So injector runs, and it will run message control commands. So this is running on a mainframe environment. In fact, I could show you what that looks like. Let's see here. Let's see if I can get this up. There we go. So if I connect in here to the mainframe, let's see if I can remember my password. And if I go into SD, that's probably hard to see. See color scheme. If I go in here and I go and show the job output, or actually, let's see, we want to run this whole command here. So we're going to run this exact command in the same place, and it comes out back, and it's going to run. It shows there's a bunch of stuff running, right? If I look at the log, let's see. See here, I'm the only user logged in right now. So, and actually I wasn't logged in, so this output wouldn't have had any output anyways. I want to say a huge thank you to Wawa's Hacking Fest for having me come and give this talk. I was really nervous about going to the physical conference just based on all the news that's going around. So I'm super happy they were able to pull off this virtual conference. It's been great. Obviously, I spent a lot of time putting this network job and figuring out and understanding network job entry. So it was being able to give this talk is huge for me, because I really wanted to talk about this for a while and give a real detailed deep dive into the protocol. I want to say thanks to the Computer History Museum. They scan all these old pamphlets. All the graphics that you saw throughout the talk were from old IBM pamphlets from like the 70s and 80s or older. Even the background was from an old tape drive pamphlet. And if this talk was interesting to you in any way, then and you want to learn more, or you wanted more detail than I was able to talk about, I would go read the proof of concept or GTFO issue 12, which goes into a lot more detail around how to use this and how you can take advantage of this. If you want, I mean, there's no reason why you couldn't use MSF Venom to generate big endian smalls payload, the high-level assembly payload, and then use and submit that with this and get a root shell from that. Right? There's no reason that wouldn't work. But I think that's it. That's all I've got, and thank you for having me.
Awesome, Phil. Thanks for being here. I'm going to follow up with you in the next week or so to have you come back and do this as a webcast for a larger audience.
I would love to.
So I would say about a month or two from now, because we're going to stagger them out so that way we can get this information out to a wider audience as well.
Great.
So thank you for being here. All right, everyone.
And, I'll be in the chat. I'll be in the chat for a bit if anyone has any questions. But thank you very much. Thanks for having me.